Mnn be the set of all matrices n by n. Let n be greater than 1 and suppose that T is a linear transformation that maps an n by n matrix to its trace. That is, T of A equals trace of A. What is the dimension of the kernel of T? To start this problem, we need to know the dimensions of the vector spaces. Here we have R, which means that it is R1. Here, however, we are not yet sure what the vector space for an n by n matrix is. To find this, we will do some examples. Our original problem stated that T was a linear transformation that mapped Mnn to R1. To find the dimension of the vector space for Mnn, we will do two examples. The first example is for a 2 by 2 matrix. For a general 2 by 2 matrix A, B, C, D, we can see that the dimension is 4 by rewriting it like such. If you multiply out these coefficients by these matrices, you will arrive back at the original matrix A, B, C, D. Therefore, we have a basis for the vector space if we rewrite these 4 linearly independent matrices. Since there are 4 of them, once again, the dimension is 4. Since we have an n by n matrix, we're going to have to see a pattern by doing another example with a 3 by 3 matrix this time. If we have a matrix A, B, C, D, E, F, G, H, I, and we rewrite it like we did before, we will have A times the matrix with a 1 in the upper left corner, plus B times the matrix with a 1 in the first row, second column, plus C times the matrix with the 1 in the first row, third column, and so on until we've gotten to I. Basically, we'll have the same format of the matrix, but you'll multiply D with the matrix in this having a 1 in this position, and E with the matrix having a 1 in this position, F with the matrix having a 1 in this position, G with the matrix having a 1 in this position, H with the matrix having a 1 in this position, and I with the matrix having a 1 in this position. If you were to count out all the different matrices that you would form there, you would get 9. So the dimension of the vector space for a 3 by 3 matrix is therefore 9. So far we have established a general pattern. For an n by n matrix, the dimension of the vector space is n squared. Therefore, we can rewrite this transformation like so. You're going from Rn squared to R1. Any transformation can be rewritten as a matrix. Let's call our matrix A. For matrix A, you have a certain number of rows and columns which correspond to these numbers here. The 1 is the number of rows, so there is 1 row. The n squared is the number of columns, so there are n squared columns. Now we have the matrix and its dimensions. We also know that the rank of A plus the null space of A equals the number of columns of A. There are certain terms that we already know. We know that the number of columns of A is equal to n squared because we just stated that up there. For the rank of A, we need to see how many linearly independent columns there are. Since there is only one row, if you imagine that there are certain numbers in this matrix, we can only have one linearly independent column because we don't have any rows underneath to put more linearly independent columns in. So the rank of A is 1. That leaves us to solve for the null space. Therefore, the null space of A, which is just another way of stating the dimension of the kernel of A, is equal to n squared minus 1. And that is your final answer.